So now let's move on to something a little bit more useful than skip and abort. Let's look at assignment to a variable, and we're going to say assignment to a simple variable, and what that means will become clear later on. So let's start with an example. Here's a code segment. The precondition is that x is equal to 5, y is computed as x plus 1, and then we want to be in a state where y is greater than 3. Is this a correct code segment? There is a couple of ways of answering that question. You could informally say, well, by just looking at it, it's obviously true. If x is equal to 5, then y will become 6, and 6 is obviously greater than 3. You could also informally compute the weakest precondition, which informally we know is x greater than 2. Why? Because x has to be greater than 2 if you want y, which is 1 greater, to be greater than 3. And notice that then you can informally determine that x is equal to 5 implies that x is greater than 2. That's one of those DA things. Or you can formally prove this through, for example, an equivalence proof. But how do we formally define the weakest precondition of some expression being assigned to y? The expression here is denoted by the funny looking e if we want to end up in a state where r is true for any expression e and any predicate r. So let's look at this again. Now here I've replaced y by x, and x just represents an arbitrary variable. Okay, so what are our key tools to be able to do this? Well, first of all, if the expression e is an invalid expression, then your program will abort, and if the program aborts, then it will not complete in a finite amount of time, and therefore it will never reach the point where you want r to be true. We need a way of saying the expression must be true, and for this we introduce the function valid of e. Also, we introduce a predicate r super x sub e with parentheses around it. What does that denote? Well, it's the predicate r, the postcondition, but every free occurrence of x is replaced by the expression. What free occurrence means we will illustrate a little bit later on. The definition then of the weakest precondition of the expression e being assigned to x, leaving you in a state where r is true, is defined as the expression must be valid, valid of e, and the predicate r with every free occurrence of x replaced by the expression e. So here we've repeated that, and let's now use that with the code segment that we discussed earlier. Let's look at the weakest precondition of y being replaced by the expression x plus 1, leaving you in a state where y is greater than 3. And instead of doing this informally, we're now going to do this formally. So here let's first identify what the expression e is. It is the expression x plus 1. And let's clearly identify what the postcondition r is. And then if you simply apply the definition, you ask yourself the question, is x plus 1 a valid expression? Obviously it is, so that will evaluate the true. And then you have r. Now, the variable to which we assign is y, so instead of x we have a y, a super y. And then we need to replace that by the expression e. And notice that the expression e is x plus 1. If you then go and you simplify this, you notice that x plus 1 is a valid expression, so that becomes true. And x plus 1 greater than 3 is the same as x is greater than 2. Then you can do and simplification, and you find out that the weakest precondition is x is greater than 2. Let's look at another example. This is actually an example that showed up in the launch. Recall that we started with 0 less than or equal to n there as a precondition for the whole program. The first statement was that 0 was assigned to s, And then we claimed that we ended up in a state where s is equal to 0 and 0 is less than or equal to n. Now we can now formally prove this correct. How do we do it? Well, we know that x has to imply the weakest precondition s comma r. We can instantiate what s and r are. S is the assignment of 0 to variable s, and yes, of course, it's a little unfortunate that we're using s in two different ways. We want to end up in a state where s is equal to 0 and 0 is less than or equal to n. We now know how to evaluate that. We know that we need to take the post condition s equals 0 and 0 less than or equal to n and replace every occurrence of variable s with the expression 0. When we do that, we get what's on the right here of the implication. S has been replaced by 0. And at this point we also go and instantiate q. And then we notice that through identity, commutativity, and simplification and implication simplification, this is true. Where does that come from? Well, we go into the details in the next slide, but let's start here. 0 equals 0 is an identity, so that's true. You can then apply and simplification, but for and simplification we really want true to be on the right of the and operator. So for that we apply commutativity. Once we do that, we can apply and simplification. At that point we end up with 0 is less than or equal to n implies 0 is less than or equal to n, and that of course is true. Notice that we've now systematically proven that code segment correct. So there is no more doubt about whether this code segment actually is correct. Alternatively, we can look at it this way. We know that before the assignment of 0 to s, the weakest precondition of the statement leaving you in a state where r is true has to be true. Otherwise, executing s equals 0 won't put you in the desired state. We can then evaluate the weakest precondition, which we just now saw was 0 equals 0 and 0 less than or equal to n. That's through instantiation, and then you replace every occurrence of variable s with 0. And then you notice that q is true just before the weakest precondition has to be true. So you know that 0 less than or equal to n has to imply 0 equals 0 and 0 is less than or equal to n. And let's actually now put all of the steps in that we kind of glossed over in the previous slide. You first apply identity, that gives you a true. Then you switch that to the other side through commutativity. Then you apply and simplification. And finally you apply implication simplification. So again, we know that this annotated code segment is true. What I want you to do now is do a couple of exercises, and then I'll see you in the next video. Let's return for a second about this issue of free occurrence of x replaced by the expression e. The way we, this by the way is called textual substitution. What's going on here? Well, consider the following. We have the assignment of 0 to I, that's our command, and the post condition is that for all I between 0 and 5 we want b of I to be 0. Now if we did this naively, you would replace every occurrence of I with 0, and you would end up with this nonsensical expression on the right. For all 0, 0 less than or equal to 0 less than 5, b of 0 is equal to 0. And that's nonsense. So what's going on here? Well, the I in the quantification, the I in the quantifier is really just a dummy variable. It can be replaced by any variable you want. So if instead we replace it by the variable j, then we get this. And then notice that if 0 is assigned to I, we can do the textual substitution. It is now any occurrence of y that was bound previously to the quantifier has now been replaced. And then we can replace every free occurrence of I with the expression 0. Now it happens to be that there is no free occurrence of I in this expression, and therefore we simply get the expression itself back again, which of course is correct. Okay, hopefully you're catching on to this assignment. So hopefully you're now getting a feel for what it means to do an assignment to a simple variable and how to compute its weakest precondition.